Let's drift softly through the cosmos and tug on one of physics' strangest threads. Why light of all things has a hard speed limit. The answer is yes to more than one of those. Before we can ask why light has a speed limit, we need to be clear on what's actually doing the speeding. Meet the photon, a tiny packet of energy that always moves, never rests, and doesn't carry mass in the usual sense. It's not a marble, it's not a pea, it's something stranger and more elegant. Photons behave like particles in how they deliver energy, yet they also act like waves, not ocean waves or a ripple in a rope, but waves of electric and magnetic fields locked at right angles and marching forward in perfect step. It's physics yoga, two fields, each driving the other, self-propagating through emptiness. Crucially, these waves don't require any substance to travel through. Sound needs air, water waves need water. Light just. That's why the sun, some 150 million kilometers away, can warm your face. Its photons cross the vacuum without a single pit stop. And light doesn't come in one flavor. Visible light, the narrow band our eyes catch, is a tiny sliver of the full electromagnetic spectrum. Imagine a piano that stretches for kilometers. The keys we can play are only a small cluster near the middle. On the long wavelength, low energy end, you'll find radio waves, lazy, sweeping undulations that can be meters to kilometers long. On the short wavelength, high energy end, sit X-rays and gamma rays, sharp, intense oscillations, born in hot, violent places like exploding stars and nuclear reactions. In between, live microwaves and infrared warmth. Plus, ultraviolet. The reason sunscreen exists, despite their differences, all these members of light's family share the same vacuum speed. Not pretty fast, not as fast as you push them, but a precise constant written into nature, 29,999,458 meters per second, just under 300,000 kilometers every second. It's a number so large it feels like nonsense. Ask, how fast? And the universe shrugs. Yet, to put that pace in bedside terms, in one heartbeat, light could lap the Earth several times. Yet it doesn't always move that quickly. In a vacuum, the track is clean, but inside materials, water, glass, diamond, light's progress is delayed. Not because photons get tired, but because they interact with atoms, get absorbed and re-emitted, nudged and redirected. The overall journey slows, even though between those microscopic encounters, each photon still races at nature's top speed. That delay produces refraction, the bending of a ray as it crosses from one medium to another. It's why a straw looks kinked in a glass, and why diamonds sparkle so fiercely. Different wavelengths are slowed by different amounts, so colors separate and dance. Speaking of color, what we perceive as red or violet is simply our brain labeling different wavelengths. Longer waves feel red to us, shorter ones feel violet. Your eyes house cone cells tuned to overlapping bands, and your brain decodes the blend into a smooth, bright world. The apple isn't intrinsically red, it reflects a chunk of wavelengths we tag as red and swallows the rest. Here's another oddity. Photons have no rest mass. That isn't a poetic flourish, it's a rule. A photon that isn't moving doesn't exist. There is no at-rest cyst for light. Motion is the condition of its being. All of this gives us a working picture. Light is energy packaged into photon quantity, also describable as ripples of electromagnetic field traversing space with a universal speed, sometimes delayed by matter, often bent, reflected, scattered, but never actually resting. For most of human history, people assumed light arrived instantaneously. You lit a flame, the room brightened. The sun rose, day began. Why imagine a delay you couldn't detect? Empedocles guessed light might take time, but Aristotle's opinions tended to stick. and instantaneous light held sway. In the 1600s, Galileo tried to test the question with a charmingly optimistic setup: two covered lanterns on distant hills. He would uncover his lantern. As soon as his assistants saw it, they would uncover theirs. Galileo measured the interval between sending and receiving the flash. The trouble is, reaction times are slow, tenths of a second, while light crosses a mile in microseconds. Unsurprisingly, he concluded that if light speed is finite, it's too fast for that method. Still, the seed was planted. Perhaps light does take time. A few decades later, Ola Römer noticed something peculiar while timing the eclipses of Io, a moon of Jupiter. Sometimes Io's on time, sometimes it's late. Römer reasoned the delays weren't Io being sloppy. The Earth's changing distance from Jupiter was altering the light's path length. When Earth is farther, the light takes longer to arrive. From this shift, he estimated how long light needs to cross Earth's orbit, the first compelling evidence that light speed is finite. That was revolutionary, not exact, but decisive. Light isn't instant. It moves, and movement requires time. The question moved from, is there a delay, to how much? In the 1800s, Hippolyte Fizeau brought the question from the sky down to apparatus: a beam, a toothed wheel, and a mirror miles away. Light passes through a gap, reaches the mirror, returns, and if the wheel is spinning fast enough, the returning beam meets a tooth and gets burned. Adjust the wheel's speed until the beam vanishes. With distance and rotation rate known, you can compute light speed. Fizeau got a value in the right ballpark. Léon Foucault refined the method with rotating mirrors, boosting precision and showing a crucial detail: light moves slower in water than in air, evidence that materials really do delay its progress. Then Albert Michelson pushed accuracy to new heights with long baselines, exquisite optics, and meticulous timing, work that ultimately earned him the first American Nobel Prize in physics. By the late 20th century, we went one step further. Rather than measuring light speed, we defined our ruler by it. Since 1983, 1 meter has been defined as the distance light travels in 129,450. Isn't just a number we estimate, it's a standard we build the rest of measurement upon. This shift quietly admits something profound. The constancy of light speed is more fundamental than our human-sized rods and clocks. With the historical groundwork laid, the natural next question is why the universe chose this value. Not 300 million ms, not infinity, but exactly the constant that tumbles out of nature's equation. Enter James Clerk Maxwell. In the 1860s, he gathered the scattered discoveries of electricity and magnetism, Faraday's coils, Coulomb's forces, the behavior of charges and currents, and compressed them into 4 elegant equations. You don't need to see their symbols to appreciate their punch. Combine them, and they predict a self-sustaining wave. Whenever electric and magnetic fields wiggle in the right way, a disturbance propagates through empty space. Do the algebra, and those equations also predict a speed for that wave. A speed determined entirely by 2 constants that describe how electric and magnetic fields behave in vacuum. Plug in the measured values, and out pops 299,792,458 millisA. Maxwell realized the punchline: that wave is light. Not a coincidence, not a numerical accident, a profound identification. Light is an electromagnetic wave, and its speed is dictated by the properties of space itself. This insight reframes the why of light speed. Isn't arbitrary. It's baked into the structure of the vacuum via those field constants. Change the vacuum's electrical or magnetic stiffness, and you'd change the speed of light and with it, the character of the universe. With Maxwell, the stage was set for the next leap. If light speed is fixed by the vacuum, and the equations say the same speed for everyone, what happens when observers themselves are moving? That puzzle fell to a patent clerk with a knack for asking the uncomfortable question. In 1905, Albert Einstein proposed special relativity. Its core postulate sounds simple, but upends common sense. The speed of light in vacuum is the same for all observers, regardless of their motion. You on a fast train, me on a quiet platform, a flashlight beam fired from either, will all measure the same. For that to be true, reality flexes. Time dilates. Moving clocks tick more slowly relative to stationary ones. Lengths contract. Objects shrink along the direction of motion as their speed climbs. And simultaneity, the idea that two separated events can be at the same time, becomes observer-dependent. None of these are optional illusions. They're built into how space-time preserves the light speed rule. Push harder, and another wall appears as a massive object accelerates toward. Getting each extra bit of speed costs more energy than the last. In the limit, the energy required diverges toward infinity. Translation: anything with mass can approach but never reach it. Light, being massless, isn't bound by that barrier. It is the barrier, and there's a deeper comfort here. The speed limit protects causality. If signals could outrun light, you could see an effect before its cause or send a message to your past self. Paradoxes sprout everywhere. By locking the maximum signal speed, the universe keeps cause ahead of effect, and logic holds. Relativity gives us a beautiful tool for thinking about influence. The light cone, picture an event. Say, you striking a match in a field at midnight. From that instant, a sphere of light expands. Everything inside that outward growing bubble can be reached by your signal eventually. Everything outside cannot, not yet. That expanding region traces your future light cone. Flip the arrow. The only events that could have influenced you at the moment the match struck are those whose light had time to arrive. Your past light cone. The cone isn't a stylistic diagram, it's a boundary between possible and impossible influence. This has lovely consequences for astronomy. Look up, and you're always seeing the past. Alpha Centauri's light left more than 4 years ago. Andromeda's, roughly 2.5 million years. Galaxies near the edge of the observable universe. Billions of years. Telescopes are time machines because light's limit is real. The same limit structures technology. A signal to a Mars rover takes minutes, one way. There is no true live joystick driving from Earth. Fiber optic data sprint at a respectable fraction. But the world is big. Even Zoom must obey physics. Far from being a nuisance, the limit gives us order and a way to read history painted in photons. It's the reason we can reconstruct the early universe from ancient light, and the reason messages don't arrive before they're sent. People naturally ask, could anything outrun light? Theoretical tachyons would only exist faster than and could never slow to or below it. But no experiment has ever found them, and if they carried information, causality would crumble. Quantum entanglement is spookier. Measure a particle here, and its entangled partner far away shows perfectly correlated behavior instantly. Tempting to call that faster than light, but you can't control the outcomes to send a usable message. Correlation isn't communication. Remain safe. There is a context where something goes faster than light in a material. Light speed in water or glass is lower. A charged particle can plow through that medium faster than light can, producing a blue glow called Cherenkov radiation, an optical sonic boom. No rule is broken. The universe in vacuum stands untouched. What about science fiction shortcuts? Miguel Alcubierre's warp bubble solution to Einstein's equations allows space-time to contract in front of a ship and expand behind it, carrying the ship effectively faster than light without locally breaking. The price tag is brutal. Negative energy densities, exotic matter we don't know how to make, and stupendous energy requirements. Transferable wormholes raise similar issues: stability, exotic matter, and time paradox headaches. Even if such structures existed, they'd be shortcuts through the fabric, not local violations of. Every credible path we've imagined either demands ingredients we don't have or preserves the light speed rule once scrutinized closely. The speed of light isn't only a cosmic curiosity, it threads through your day. Your phone leans on pulses of light racing through fibers under streets and oceans. Those bits still need time to cross the world. GPS works only because engineers correct for relativity. Satellites' clocks tick differently thanks to their speed, special relativity, and weaker gravity at altitude. General relativity. Left uncorrected, your location would wander kilometers per day. Your own vision is photon work. Light refracts through cornea and lens, focuses on the retina, triggers chemical changes in rods and cones, and is stitched into a coherent scene by your brain. Lenses, from eyeglasses to microscopes to cameras to telescopes, are deliberate manipulations of refraction, slowing and bending different wavelengths by design. Microwaves heat food by jiggling water molecules. Radio and Wi-Fi are just long wavelength light moving information at near. X-rays peer through soft tissue. MRI dances with electromagnetic fields to map the inside of you. Zoom out, and light becomes our historian. The cosmic microwave background, the oldest light we can see, carries a whisper from when the universe first became transparent, roughly 380,000 years after the Big Bang. Those photons have been traveling ever since, stretched into microwaves by the expansion of space, arriving gently in our detectors to tell us what it was like back then. From photosynthesis to circadian rhythms, from starbirth to your bedside lamp, photons knit together energy, information, and time, always moving, always on schedule, always honoring that quiet limit that keeps the universe sensible. There's a quiet magic in that letter. We usually talk about it as a speed, but it's also a translator, the bridge that lets space and time speak the same language. You've seen it hiding in plain sight in event. Mass can be viewed as tightly packed energy, and the conversion rate between the two is set a very large number that explains why tiny amounts of mass can unleash astonishing energy. In relativity, appears again as the scale that keeps space-time bookkeeping consistent. If you've ever heard of the space-time interval, you can think of it as a kind of cosmic distance that blends space and time into one invariant measure. Two observers may disagree about how much space separated two events or how much time passed, but they will agree on this blended interval. It's like the universe saying, you can slice this loaf at different angles, but the loaf itself doesn't change. In theoretical work, physicists often say, not out of laziness, but to make the unity between space and time explicit. When distances and durations share units, many formulas untangle and reveal their structure. This natural units view reminds us that a meter and a second aren't separate things in nature. We made them separate for convenience. Under the hood is the conversion factor that stitches them back together. Even our everyday language carries this fusion. We measure astronomical distances in light years, a time word used as a length. When you say a galaxy is 10 million light years away, you're really saying its light has needed 10 million years to get here. And embedded in that simple sentence is the whole philosophy of relativity. Space is traveled through time, and time is measured by space as the rhythm section keeping both on beat. So far, we've let space and time bend to keep light's speed constant. General relativity adds a deeper lyric. Gravity isn't a force tugging across distance. It's the geometry of space-time itself. Einstein's favorite thought experiment starts in a falling elevator. Inside, you feel weightless. Objects you let go of float right beside you. Locally, falling under gravity is indistinguishable from drifting in deep space with no gravity at all. This equivalence principle points to a radical idea. Massive objects don't pull so much as they curve the stage on which motion unfolds, and everything, planets, pebbles, and yes, photons, follows the straightest possible paths within that curved stage. We call those paths geodesics. Light follows special geodesics called null paths. And because it must always move at speed, space-time's curvature shows up as a deflection of light's route rather than a change in its speed. That's why starlight grazing the sun bends by a small but measurable angle, and why clocks in stronger gravity tick more slowly than clocks higher up. This isn't just poetic. We correct for it daily. GPS satellites ride higher in Earth's gravitational field and move quickly relative to the ground. Special relativity slows their onboard clocks. General relativity speeds them up due to weaker gravity. Engineers calibrate both effects, so your map pin lands on the right street. Another gentle consequence is the Shapiro delay. Light passing near a massive body takes a smidge longer to arrive than it would in flat space, not because photons get sleepy, but because the geometry they traverse is subtly stretched. In this picture remains the local limit everywhere. The fastest any traveler's signal or influence can go, while space-time itself sets the lanes, the curves, and the timing of the journey. Curved space-time turns the universe into an optical artist. When mass gathers in galaxies or clusters, it can act like a lens, bending and focusing the light from still more distant objects. This gravitational lensing can produce arcs, duplicated images, even near-perfect rings if alignment is just right. The effect isn't only beautiful, by measuring how background galaxies are warped, astronomers weigh the lens that did the warping, including matter we can't see directly. That's one of the strongest pieces of evidence for dark matter. The gravity we infer from lensing exceeds what visible stars and gas can supply. Sometimes, lensing works like a cosmic magnifying glass, boosting the apparent brightness of a faint, faraway galaxy so we can study it in detail we'd never otherwise reach. It also acts like a clock. Light taking different bent paths around a lens arrives at slightly different times, letting us timestamp the geometry and expansion history of the universe. At smaller scales, light can echo around dense objects in more subtle ways. Starlight that skirts a compact remnant like a neutron star or black hole can be deflected enough to change the timing and spectrum we observe, revealing the mass and spin of the object doing the bending. Even without fancy equations, the idea is intuitive. Picture space-time as a flexible fabric. Heavy objects dimple the sheet, light follows the contours. It doesn't slow down locally, the limit is honored everywhere. But the route becomes longer or differently angled than it would be on a flat sheet. Gravitational lensing is the sky's way of letting mass sketch with photons, tracing invisible structures with visible strokes. Every arc and ring is a reminder that light is both messenger and medium, painting the shape of what it passes. Follow gravity's geometry to its extreme, and you arrive at black holes, regions where space-time is curved so severely that there's a point of no return. The event horizon, outside the horizon, a photon can still flee if it's aimed just right. Closer in, at the photon sphere, light can orbit in precarious circles, like a marble skimming the lip of a bowl. Cross the horizon, though, and every path the geometry allows points inward. It's not that light slows down inside, rather the shape of space-time itself funnels all possible paths toward the center. The escape velocity at the horizon equals nothing moving at or below that speed can get out. Surrounding many black holes is an accretion disk, hot, bright gas spiraling inward, and above it, magnetic fields can launch jets of particles at relativistic speeds. From far away, clocks near the hole look sluggish. Their ticks stretch out, gravitational time dilation, so a burst of light emitted near the horizon can be redshifted into softer wavelengths by the time it reaches us. Even the silhouette of a black hole, the shadow, is a triumph of light's constancy. Photons grazing close by are deflected, some captured, some flung around in looping paths, carving a dark core encircled by a bright photon ring. Nothing in this drama violates the cosmic limit. It celebrates it. The horizon is defined. The brighter the dance in the disk, the more it advertises the geometry light must obey. To watch a black hole is to watch photons tell the truth about space-time under extraordinary conditions. A truth written in bending paths, stretched colors, and delayed arrivals, all choreographed by a speed that never changes and a stage that does. Black holes also brought an unexpected marriage: gravity, thermodynamics, and quantum theory. Jacob Bekenstein argued that a black hole should have entropy, a measure of information or microscopic disorder proportional to the area of its horizon, not its volume. Stephen Hawking followed with a startling calculation: quantum fields near the horizon imply black holes radiate very faintly with a temperature inversely related to their mass. This Hawking radiation means black holes can slowly lose mass over absurdly long timescales. The formulas weave together fundamental constants. Is not a bystander. It sets scales, ties units, and helps define how energy, time, and information convert in the most extreme theaters. The Bekenstein bound hints at a limit to how much information can be packed into a region, again, in the mix. These ideas feed into the holographic intuition. Perhaps the deepest bookkeeping of a region lives on its boundary, not inside. A whisper that geometry, information, and light are braided more tightly than we guessed. The details are still an active frontier, but the melody is clear. Wherever we push, physics returns as the tempo that keeps quantum notes and gravitational harmonies in time. Even paradoxes like the information problem, where the details of what falls into a black hole are truly lost, are framed by what light can and cannot carry out across the horizon. The speed limit sets the rules of communication. Thermodynamics and quantum fields try to write their stories within those rules. Out of that tension, modern theoretical physics draws some of its most luminous questions. If gravity curves the stage, the universe itself is a changing theater. On the largest scales, space expands. Galaxies aren't flying through a fixed void like shrapnel. Rather, the distances between unbound structures grow with time as the cosmic fabric stretches. Light carries the receipt. Wavelengths emitted long ago arrived today, stretched, redshifted, not because source and observer necessarily raced apart through space, but because the space between them expanded while the photon was en route. This is why we don't talk about galaxies moving faster than light, when very distant ones recede superluminally in a cosmological sense. Nothing locally outruns. Instead, the metric that measures distance evolves. Rulers get longer between ticks. Photons still plod along locally, but the road lengthens beneath them. There are horizons in this picture too. The particle horizon marks the farthest distance from which light has had time to reach us since the universe became transparent. The cosmic event horizon, if expansion accelerates, can define a limit beyond which events will never be able to send us light, no matter how long we wait. It's a gentle but humbling thought. There are parts of reality forever outside our light cone, not due to impatience, but because the geometry itself says those stories can never arrive. Yet within our observable patch, photons keep perfect books. The amount of redshift encodes how much the universe has expanded during their journey. The pattern of tiny temperature ripples in the cosmic microwave background encodes the seeds of today's galaxies. Everywhere we look, light reports what happened along its path: distances stretched, times dilated, structures grown, all without ever breaking its steady pace. How do we turn those whispers into measurements? Astronomers build a distance ladder, stitching together methods that work at different ranges. Nearby, geometric parallax lets us triangulate a star's distance by watching its apparent position wobble as Earth orbits the Sun. Farther out, certain variable stars pulse with periods tightly tied to their brightness. Measure the period, infer the true luminosity, compare with how dim they appear, and you get distance. Beyond that, Type 1a supernovae, stellar explosions with fairly standard peak brightness, serve as beacons in remote galaxies. Each rung relies on light behaving consistently: inverse square dimming with distance, characteristic colors, identifiable spectral lines. Those spectral lines are light's fingerprints, imprinted by the atoms that made or filtered the photons. When lines shift toward the red, we read recession. When they split or broaden, we read motion, temperature, and environment. Large surveys map millions of galaxies, revealing a cosmic web, filaments and clusters interconnected across scales, all traced by where starlight and gas glow. Even the dark gaps aren't empty. Lensing shows mass there, and when we need exquisite precision, we turn to interferometry, combining light waves from separated telescopes to synthesize a giant virtual mirror. The trick works because the crests and troughs of light add and subtract in predictable ways. Align them correctly, and detail emerges far beyond what a single instrument could resolve. Whether it's a nearby exoplanet dimming its star by a whisper, a percent, or a galaxy so far away its light set out before Earth had oceans, the method is always the same. Respect light's limit, learn its dialects, and listen carefully. Back on Earth, materials teach light new steps. The refractive index tells how much a medium delays and bends light relative to vacuum. Dispersion, varies with wavelength, spreads white light into rainbows, and lets prisms, gratings, and even soap bubbles turn thickness and angle into color. There's nuance here: the phase velocity, how quickly a wave crest seems to move, and the group velocity, how fast a pulse, and with it information and energy travels, aren't always the same. In some exotic conditions, phase velocity can exceed, but that never carries information faster than light. The group velocity and signal front still respect the limit. Experiments have even produced slow light in ultra-cold gases where group velocities drop to bicycle speeds. It's a delightful party trick and a potent probe of quantum matter, but it doesn't dent the cosmic rulebook. Engineers exploit dispersion to build fiber optic networks, crafting wavelength division multiplexing that sends many colors down the same glass without tripping over one another. Metamaterials, structures engineered smaller than a wavelength, can bend light in unusual ways, even producing an effective negative index over certain bands, leading to superlenses that beat conventional resolution limits at close range. Yet in every case, when you ask about the ultimate speed for information, the answer bows. The material can delay, detour, or reshape the journey. It can never rewrite the maximum pace. Watch a rainbow flicker on a soap film, and you're seeing a living interference pattern, a dance between phase and geometry that quietly encodes the same principle as your internet link and a radio telescope. Half a worldwide light is flexible in route, unyielding in limit. If you build machines for thinking, becomes a daily constraint. Inside microchips, information moves as electrical signals along metal interconnects, or as light in specialized photonic links. As transistors have shrunk and clock speeds climbed, designers have found a surprising foe: distance. When a clock tick lasts a few hundred picoseconds, the time it takes a signal to cross a chip, or worse, to go from one server to another, becomes a first-order design problem. You can add bandwidth with wider buses and parallel channels, but you cannot cheat latency. The speed of light means a data center on one continent can never feel local to a user on another. Content has to be replicated nearer to where it's needed. Financial traders once chased microseconds by choosing straighter fiber routes. Then they turned to microwave relays through air because signals move faster there than in glass. Still sits at the top of every budget. Undersea cables carve great arcs to balance geography, politics, and physics. Each extra kilometer adds a few more microseconds. Even inside a single motherboard, engineers juggle trace lengths so that signals meant to arrive together actually do. This is Shannon's world too. How much information you can push down a channel depends on noise and bandwidth, but the earliest possible arrival of anything is governed by the light speed clock. It's humbling and helpful. You can compress, encode, error correct, and amplify. You can place servers closer, route smarter, and cache aggressively. But there's a lowest floor to waiting: the time a photon needs to do its job. In a way, that floor is a gift. It forces architecture, distribution, and cooperation, turning a global network into a web rather than a single, impossible wire. Measurement itself has been rebuilt around light's steadiness. We define distance, and we define time by atoms. The second is set by a specific number of oscillations in cesium-33's microwave transition. Tie those together with lasers, and you get astonishing rule. Interferometers use the fact that light's wavelength is exquisitely regular. Split a beam, send the halves down different arms, recombine them, and the interference fringes shift with picometer sensitivity when one arm changes length. Laser ranging to the moon bounces pulses off retroreflectors left by Apollo astronauts, timing the round-trip travel to measure the Earth-Moon distance to the millimeter. LiDAR times single-photon flights to paint 3D maps of forests and city streets on the grandest and subtlest scales. Observatories like LIGO and Virgo hold 4-kilometer arms in near-perfect alignment, watching for minuscule rhythm changes in laser light, changes caused when space-time itself stretches and squeezes as gravitational waves pass. Those detections don't just confirm predictions, they inaugurate a new sense, a way to hear cosmic events that light alone can't fully describe, yet even that hearing is read out in photons, their phases and timing telling the tale. In metrology labs, frequency combs stitch optical and microwave domains together, letting clocks talk across colors with astonishing accuracy. New optical lattice clocks promise stability that could one day sense variations in Earth's gravity from a change in tick rate across a building's floor. Threading all of it is a constant beat: photons launched, delayed, recombined, counted, distances converted to times and back again by the same unyielding factor. We didn't just measure and move on. We built our rulers and metronomes from it, and now we let light teach us how carefully the universe can be known. If light feels like a paradox, wrapped in calm certainty, the double-slit experiment is the lullaby where that paradox hums the loudest. Picture a dim source sending photons one at a time toward a barrier with two narrow openings and a screen beyond. Intuition says each photon should travel through one slit or the other and make two neat piles. But when both slits are open, the screen slowly blooms with an interference pattern, light and dark bands where probabilities and cancel, as if each photon explored both paths and interfered with itself. Close one slit and the pattern collapses to a single slit blur. Add a which path detector to learn which slit a photon used, and the interference dissolves. The very act of extracting path information trades away the delicate phase relationship that produces the bands. Nothing here outruns light or smuggles information faster than causality allows. The pattern emerges only after many arrivals, never from a single detection, and you can't use it to send a message to someone watching the other slit. What the experiment does, whispers that light's identity wave particle isn't either or, it's both and, depending on how gently or insistently we ask our question. The speed limit still rules every arrival time on the screen, every tick of the detector. Interference structures are not couriers. They're bookkeeping, a statistical register of possibilities, resolving into happenings dot by dot. Drift with that thought. The universe often holds two ideas at once. A photon that travels every allowed path, a measurement that picks one, the quiet constant through all of it. The pace at which possibilities become detections, the rate at which the story writes itself, line by patient line across the screen. Where do photons get their personalities, their colors, their punch? From frequency. A photon's energy, E888. Higher frequency, higher energy. Lower frequency, softer touch. This simple line, born from Planck's work and carried by Einstein to explain the photoelectric effect, reshaped physics. Shining light on a clean metal surface doesn't just warm it. Above a certain color threshold, it kicks electrons clean out. Brighter subthreshold light won't budge them. A dim beam of sufficiently blue light will. Energy arrives in quanta, not drizzle. In that sense, light is both sculptor and storyteller for technology. Your camera sensor is a grid of tiny photosites. Photons knock electrons into motion, charges accumulate, electronics read out a picture. In solar panels, photons lift electrons across a semiconductor's band gap, launching a current that becomes power for homes and cities. In photo multipliers and single photon avalanche diodes, one photon triggers a measurable cascade, letting astronomers count whispers from galaxies, and LiDAR measure distances by timing a handful of returning quanta. None of this lets us dart past the speed limit. The timestamp on every detection is a time of flight story told at plus whatever detours and delays the medium contributes. Even the blue of a screen pixel is a negotiation between frequency and material. The device emits photons clustered around a target wavelength. Your eye's cones interpret the cocktail as blue, that your mind turns a rain of quantized impacts into a seamless wash of color is part biology, part physics, part miracle of averaging. Beneath it all, the rhythm remains. Frequency sets energy, energy sets what matter can do, and the journey from source to sensor moves on the same steady clock that keeps causality tight. If you've ever seen the sharp red line of a laser trace dust in a dark room, you've watched coherence at work. Photons marching in step, same color, same phase, same direction. Lasers arise from stimulated emission. An excited atom, nudged by an incoming photon of just the right frequency, drops to a lower state and emits a twin, same frequency and phase. Put many such atoms in a cavity with mirrors, encourage the right light to bounce back and forth, and a cascade builds, a beam as orderly as a metronome. Coherence is a gift to measurement and medicine. It lets interferometers sense changes far smaller than an atom. Surgeons cut tissue with exquisite precision, and fiber networks carry dense, phase-encoded data across ocean. Pulse. A laser and you get another toy. a packet of light short enough to freeze ultra-fast chemistry to probe electrons on their natural time scales. Send those pulses through matter, and dispersion stretches them, each color lagging a little differently. Engineers pre-compensate with chirps, designing pulses whose colors are staggered so the medium compresses them back to a tight spike at the target. Through these tricks, we can shape light's envelope, but we don't move information faster than light. Inside a material, the phase velocity can exceed, but that's the speed of a crest's wiggle, not the speed a new signal can travel. The signal front, the very first hint of a change, stays at or below. Coherence grants us clarity, not permission. It turns photons into a chorus, not a loophole. Drift with that, the straighter the choir sings, the finer the detail we can hear. But the tempo, the ultimate beat that defines what on time means, still belongs. Light has a preferred wiggle. In an electromagnetic wave, the electric field oscillates in a plane as the wave advances. Polarization labels that orientation. Sunlight is a jumble of polarizations. A laser can be disciplined, horizontal, vertical, circular, or elliptical. Your polarized sunglasses exploit this discipline. Glare from water or roads is often horizontally polarized by reflection, so vertically oriented filters dim it without darkening everything else. Liquid crystal displays twist polarization on demand, turning pixels on and off with tiny electric nudges. In the lab, polarizers and wave plates act like gentle coaches, rotating or filtering the electric field's dance to prepare light for interferometers, quantum experiments, or fiber links. In the cosmos, polarization writes subtler prose. Scattered sunlight makes blue sky weakly polarized. Point your camera through a polarizer, and the sky deepens as you rotate the filter to align with that hidden order. Starlight passing through aligned interstellar dust picks up a polarization signature that reveals magnetic fields between the stars. Even the cosmic microwave background carries a faint polarized pattern that encodes ripples in density and the geometry of early expansion. Across all of these scenes, polarization changes what we see and how clearly we see it, but not how fast a message can travel. A rotated electric field does not slip past the limit. The time it takes for a polarized pulse to arrive remains a function of distance, refractive index, and the unwavering yardstick. In that sense, polarization is character, not speed. It gives light a voice with accent and emphasis, a way to carry extra layers of meaning, while the metronome underneath, the rate at which syllables can reach us from afar, ticks with the same patient constancy as always. Where light meets edges, it paints with softness. Diffraction, the tendency of waves to spread when squeezed through small openings, sets a resolution limit for all imaging. A circular lens doesn't focus a point to a perfect dot, it makes an airy disk with faint rings. Two stars closer together than that disk's width blur into one unless you enlarge your aperture or combine telescopes across long baselines. That's why big mirrors matter and why radio astronomers link dishes across continents with longer wavelengths. You need a vast, effective aperture to sharpen the view. Interference sits beside diffraction like a partner in a slow waltz. Split a beam, send both halves along different paths, and reunite them, their crests and troughs, add and subtract into bright and dark fringes, exquisitely sensitive to path differences. This is how we measure nanometer shifts in mirrors, how we test optics, how we read the tiny grooves in a compact disc, and how we recover exquisite detail from starlight that would otherwise be lost. Super-resolution tricks, near-field probes, computational deconvolution, metamaterial superlenses stretch what's possible, especially at close distances where evanescent fields carry sub-wavelength detail. Yet nothing in this suite of artistry opens a tunnel through causality. The smallest feature you can resolve in a distant object still bows to diffraction. The earliest moment you can know about a change still bows to time of flight. You can gather more light, average longer, move to shorter wavelengths, and compute smarter, all worth. But the first photon that could tell you something new still had to leave, travel, and arrive. The universe offers clarity in exchange for patience. Diffraction sketches the price of sharpness, sets the floor for when a new sketch can begin. Everyday devices are photon markets where light and matter barter energy. In a solar cell, a photon with energy above the semiconductor's band gap excites an electron from the valence band into the conduction band, leaving behind a hole. An internal electric field separates the pair before they can recombine, sending the electron one way and the hole the other. The flow becomes current. If the photon's energy is too low, it passes through too high, and the excess is lost as heat. That's why bandgap engineering, stacking materials tuned to different parts of the spectrum, boosts efficiency. Flip the script and you have an LED drive electrons and holes together in a suitable semiconductor. They recombine by emitting a photon with energy set by the bandgap, a direct pipeline from electrical work to colored light. Add phosphors or layered structures, and use scoped white light for homes, offices, and screens. Lasers add resonant cavities and inversion, giving coherence. None of these exchanges cheat causality or light speed. They play inside it. A solar panel doesn't store a photon's speed, it stores its energy. An LED doesn't spit photons out faster than it produces them with a controlled spectrum and direction. Photonic circuits go further, guiding light through etched waveguides to compute or communicate with less heat than copper. Even here, delay is real. Bends, couplers, and materials impose group velocities that sit below, and the earliest bit still waits for the same final green light from physics. Let that be soothing. Technology can turn photons into power, messages, scalpels, and clocks. It cannot turn them into time machines. What it can do, with careful design, is arrange their arrivals into symphonies of utility, each note on beat. Step outside and the sky performs quiet optics. Why is the sky blue? Sunlight collides with tiny atmospheric molecules that scatter short wavelengths more efficiently, Rayleigh scattering, so blue light is redirected into your eyes from all directions, while red and green trek straighter paths. At sunrise and sunset, the sun's rays cross a longer slice of air. Blue and green scatter out of the direct beam, leaving the path to your eye enriched in reds and oranges. Ice crystals high in the atmosphere act as prismatic plates and columns, making halos at set angles around the sun, sundogs that flank it, and pillars that rise above it at low angles, all born of refraction and reflection. Rainbows bloom when raindrops act as tiny lenses, refracting and reflecting sunlight inside and back out, separating colors by dispersion so each angle corresponds to a hue. Stand still, and the arc is always the same radius centered on the anti-solar point. Move and you trace a different cone of returned light. Even mirages are physics poetry. Temperature gradients bend light so distant roads shimmer with false lakes, and inverted images float above hot surfaces. In none of these tableaus does light sprint faster than its limit. The beauty is pathwork and timing, not speed. A sunset's lingering glow is delayed not by a photon pausing, but by the geometry of the curved earth and the extra kilometers of air the rays traverse. Twilight is softness, stretched by root length and scattering, a final act where the sun has set for you, but its light, detoured still, finds a way. Let that be a gentle metaphor. Sometimes the straight path ends, and yet by a longer way around, the light still arrives. If special relativity sounds abstract, the atmosphere and accelerators make it concrete. Cosmic rays smack into upper air nuclei and spawn showers of short-lived particles called muons. At rest, a muon decays in about 2.2 microseconds. Not enough time to descend the tens of kilometers to sea level, yet detectors at the surface click with muons all day. For the muon, time dilates as it plummets at relativistic speeds. From our frame, its internal clock runs slow, buying it the extra microseconds to arrive. In particle accelerators, protons whip around rings at a hair. Each tick of energy buys a smaller and smaller increment of speed. Most of the work goes into mass energy rather than extra kilometers per second. When these particles radiate synchrotron light, the beams are so bright and tunable that entire facilities are built around their glow for biology, chemistry, and material science. Cherenkov detectors watch for the blue cones cast by particles moving through water faster than light can move in that water. A local speed limit broken without touching the universal one. All of this is a playground where engineers and physicists push right up against the edge, not to jump off, but to see how close the rules let us dance. The lessons filter down: hospital Linux that treat tumors, PET scanners that time back-to-back photons to locate tracers in the body, calibration methods that turn particle timing into exquisite rulers. Relativity isn't just a far-off starship concern, it's the reason the data match the world, the reason the counts fit the curves, the reason the experiments work the same Tuesday after Tuesday, and always the top line on the whiteboard is the same: nothing with information gets there faster than light. What about messages among the stars? If we dream of talking to distant minds, the speed of light becomes etiquette as much as physics. A hello to a planet 100 light-years away is a conversation with a 200-year round trip where every question and answer spans generations. Even nearby worlds demand patience. Commands to a rover on Mars take minutes. Returning images take minutes more. That's why we build autonomy into explorers. They think locally, we review later. For interstellar travel is the hard roof. Cleverness works below it. High-efficiency propulsion, light sails pushed by powerful lasers, fusion concepts, each tries to nibble at transit times, to turn centuries into decades, decades into humanly meaningful arcs. Still, latency is baked in. That shapes strategy: caches, near users, telescopes that compile surveys and downlink summaries, probes that decide which data are worth the precious beam time home. It shapes hope too. A signal found by SETI will not be a chat app. It will be a fossilized greeting, a pattern we interpret slowly, carefully, with the humility that our reply will be a bottle tossed back across an ocean of years. And yet this is not discouraging. Light's limit gives weight to choice. A message worth sending across decades must be crafted with care. An instrument designed to sip photons for months must be designed to last. In a world where some things are instant, it is calming to remember that the largest, grandest correspondences still take their time. The universe invites us to be patient communicators, builders of instruments that wait, readers of signals written before our grandparents were born, and perhaps writers of signals someone's great-grandchildren will read in turn. We've wandered far, and yet the path has been steady. Every detour through prisms and pulsars, through sunglasses and satellites, through rainbows, lasers, lenses, and black holes has come back to the same quiet fact: light moves with a speed the universe will not let anything outrun, and that steadfast pace is less a restriction than a design. It is the stitching that holds space and time together, the ruler we build our rulers from, the tempo that gives meaning to before and after. If you feel a little calmer holding that in mind, you're not alone. The speed of light is order in a restless world, a constant we can trust while so much else varies. It gives us sunsets that last just long enough, networks that must be thoughtfully arranged, clocks that can be tuned to hear gravity itself, and maps of the early universe traced in microwave whispers. The limit isn't a scolding finger, it's a guardrail, a rhythm section, a promise that cause will precede effect and that messages will arrive in their proper time. As we drift into the second half of our journey, we'll keep the same gentle stride, exploring how light sketches reality at the smallest and largest scales, from quantum uncertainty to the birth of elements, from the faintest galaxies to the lights by your bedside. For now, breathe in the comfort of constancy. Somewhere, a photon has just left a star. Somewhere else, one has just reached an eye. Between those two moments is a story told at exactly the same pace it has always been told, and that is a lovely thing to fall asleep to. Light carries temperature as color, and that idea quietly organizes both the night sky and your living room. Heat an ideal object, a black body in physics, shorthand, and it glows with a spectrum whose shape depends only on temperature. Cooler objects lean red, hotter ones lean blue. Stars obey this melody. A reddish star is cooler, a white or bluish star is hotter. There's a simple rule of thumb, Wien's law, that links peak color to temperature, which is why astronomers can estimate a star's surface heat just by measuring its light. We echo the same logic indoors. A candle glows around a 1,800-2,000 K and feels cozy because it leans toward amber. Old incandescent bulbs lived near 2,700 K. Warm white LEDs are tuned to mimic that. Office lighting often aims for 4,000-5,000 K to feel bright and alert. Midday daylight lands even higher. None of these temperatures mean the bulb is that hot. They describe the color mix compared with an ideal radiator. Under the hood, the spectrum is a smooth curve, richer in reds for warm light, richer in blues for cool light. Your eye and brain stitch that curve into an impression called color temperature, and your mood follows along. Amber hints at evening, bluish hints at noon. Photographers and filmmakers set white balance to tell the camera which light to call neutral. Otherwise, a face lit by warm lamps looks orange or a snowy scene looks blue. All the while, the photons themselves keep their punctual pace. A warm LED doesn't trudge more slowly, its spectrum is just shifted. A hot star doesn't sprint faster, it simply emits more short wavelength photons per second. Speed is the same, distribution changes. There's something gentle in that. The world can change its tint without changing its tempo. Night can be warm, day can be cool, stars can sing in red or blue, and the metronome underneath never misses a beat. Light is also a barcode. Atoms and molecules have allowed energies like rungs on a ladder. When electrons hop between rungs, they absorb or emit photons with very specific colors. Spread starlight with a spectrograph, a precise prism plus slit instrument, and you'll see dark absorption lines and bright emission lines at exact wavelengths. Hydrogen leaves its familiar Balmer set. Sodium etches a crisp yellow doublet. Oxygen, calcium, iron, and countless others carve signatures, letting us read a star's chemistry from light years away. This is how we know the sun contains hydrogen and helium in abundance, and how we measure the metallicity of stars to trace galactic history. The barcode also, when a source approaches, its lines shift slightly shorter in wavelength, blue shift. When it recedes, they stretch longer, red shift. This Doppler effect is precise enough that astronomers can detect a star's tiny wobble caused by an orbiting planet. The star moves toward us and away again by a handful of meters per second. Its spectral lines slide back and forth by a whisper, fold years of steady measurements together, and a new world emerges from the pattern. A planet we cannot see directly, revealed by the way it tugs on its star's light. Nothing here needs instant communication. The story is patient. Photons left that star long ago, carrying both the chemical fingerprint and the Doppler wiggle We gather them, sort them, and compare line positions to laboratory standards measured on Earth. Chemistry tells us what's there. The Doppler shift tells us what it's doing. When the shift is periodic, we infer orbits, masses, and sometimes even eccentricity. The lesson is a soothing one. If you know what at rest looks like, small changes in light can reveal motion so slight you'd never spot it any other way, motion written into color by the same constant that fixes light speed. Another way to find distant worlds is to watch a star dim. If a planet's orbit happens to cross our line of sight, it will occasionally transit in front of its star, blocking a tiny fraction of the starlight. The drop might be 1% or far less, but it's repeatable and periodic, and it creates a light curve. A gentle U-shaped dip whose depth maps to the planet's size relative to the star. Time those dips and you get the orbital period. Combine with the star's mass and you get the planet's distance from its sun. Pair the transit with the Doppler wobble from spectroscopy and you can estimate density, rock, ice, or gas. There's more. During the transit, a hair-thin shell of the planet's atmosphere can imprint extra absorption on the starlight streaming through it. By comparing the spectrum just before, during, and after transit, astronomers can tease out hints of atmospheric molecules, water vapor, sodium, methane, carbon dioxide, each leaving delicate fingerprints. In the softest whispers of data, a skyline appears around a world we'll never visit, drawn entirely from how the star's light changes by a few parts per million. The choreography depends on timing, alignment, and patience. Planets don't rush. They keep their orbits, and we keep watch. Photons do not speed up to help us. They leave the star when they must and arrive when they can. We stack many transits to lift signal out of noise, and slowly a catalog of other skies takes shape. Some worlds are blistering hot, hugging their stars in days-long years. Others circle farther out, temperate perhaps, with clouds that mute their spectral edges. The method is humble and relentless. Measure brightness precisely, fold the measurements by the suspected period, and let light confirm the rhythm. It's astronomy as meditation, regularity revealing reality. At the high-energy end of the spectrum, the universe writes in exclamation points. Supernovae announce the death throes of massive stars or the thermonuclear flash of a white dwarf pushed over a mass limit. For a brief time, a single explosion can outshine an entire galaxy, and the light curve, a quick rise, a slower fade, carries the physics of radioactive decay and expanding debris. Gamma-ray bursts are sharper still. Flashes of gamma rays lasting milliseconds to minutes, often followed by afterglows at X-ray optical and radio wavelengths. We think some come from merging neutron stars, others from collapsing massive stars forming black holes. The photon parade they release is joined by other messengers, neutrinos, ghostly particles that sail through matter almost untouched, were caught from a supernova in 1987, arriving within hours of the light, confirming pieces of collapse theory. More recently, gravitational waves, ripples in space-time from colliding compact objects, have chimed in, with follow-up light observations painting a full portrait, heavy elements forged in radioactive kilonova ejecta, fading from blue to red as opacities change. Each messenger respects causality. Each travels at its allowed pace. Together they cross-check one another. Light often arrives after the first gravitational wave wiggle because it takes time for jets to punch through surrounding debris or for shock heating to bloom. When the light does reach us, its timing and color evolution carry the fingerprints of the engine. Multi-messenger astronomy, then, is an ensemble piece. Gravity tells you when space-time shook, neutrinos whisper about the core, photons deliver the surface show. It's remarkable that so much can be known from signals that left tiny distant regions under extreme conditions. Remarkable and comforting, because even in cosmic fireworks, the rules stay steady. The fastest parts of the story are still told at light's unwavering pace. Life learned to work with light long before we learned to measure it. On land, fireflies choreograph summer with bioluminescent enzymes that convert chemical energy directly into photons, blinking in courtship codes species can recognize. In the deep ocean, where sunlight fades to black within a few hundred meters, bioluminescence becomes a language and a lure. Fish, jellyfish, squid, and plankton carry living lanterns, some to startle predators, some to attract mates, some to bait prey with glowing decoys. The chemistry varies, but the principle is the same. A molecule excited by a reaction drops to a lower energy and emits a photon with a color set by the energy gap. Plants, on the other hand, eat light. In photosynthesis, pigment protein complexes capture photons and funnel their energy toward reaction centers where electrons are boosted and set to work building sugars. The steps are quantum precise and extraordinarily efficient at room temperature, a feat that still inspires engineers trying to mimic that efficiency in solar tech. Humans, too, run on light in subtler way. As specialized retinal cells containing melanopsin signal overall brightness to your brain's master clock, helping set your circadian rhythm. Morning light tells your system to suppress melatonin and wake. Evening's dimness nudges the hormone upward, preparing sleep. This is why screen filters and warm lamps can feel kinder at night. Less short wavelength content means less circadian daytime signal at bedtime. None of these roles depend on light breaking its limit. Fireflies do not blink faster than causality allows, and plants do not smuggle energy across impossible gaps. They simply live inside the rules with elegance, turning photons into information, food, and timekeeping. It's calming to realize that biology's dances with light are patient ones, messages passed molecule to molecule, rhythms entrained by dawn and dusk, all measured out by the same ticking constant that steers starlight. Your visual system is a master of useful illusion. On a moonlit night, rod cells dominate. They are sensitive but colorblind, tuned to detect small pools of light at long wavelength. Your cones barely register. In daylight, cone cells take over, handing you crisp color through 3 overlapping channels that your brain blends into a continuous palette. Between those regimes, perception shifts. A blue sweater can look different at noon versus under a warm lamp, yet your brain applies color constancy, comparing surfaces and lighting to keep the sweater's identity stable. There's also temporal alchemy. Flicker a light fast enough, and the pulses fuse into steady glow. The flicker fusion threshold projects still images in rapid sequence, and motion appears, not because the pictures move, but because your brain knits the changes into narrative. These perceptual tricks are not errors, they're optimizations. Your brain prefers stable objects and continuous motion over chaos, so it edits raw photon hits into something coherent and useful. That's why optical illusions are delightful. They reveal the editing process. Lines look bent by context. Identical grays appear different next to black or white. Grids sparkle at intersections that aren't glowing. Gradients hide edges that pop out when contrast flips. None of this speaks to light traveling faster than itself. The arrival of photons at the retina is fixed by geometry, refractive paths. The interpretation, what your mind decides it sees, is where the creativity happens. In that sense, perception is a collaboration. Physics delivers the data on time. Your nervous system compresses, filters, predicts, and sometimes hallucinates a little to keep the world. Perhaps that's why candlelight feels calm, fewer photons, warmer spectrum, softer contrast, and a brain ready to do more soothing interpolation than frantic edge detection. Every warm thing glows. We can't see most of it, because our eyes catch only a tiny wedge of the spectrum, but the physics is universal. A hot stove radiates infrared, a campfire sprays light across red, orange, and yellow, a star pours out a black body-like curve set by its surface temperature. Planck's law tells how much energy comes at each wavelength. The Stefan Boltzmann law sums it all, saying total radiated power scales with the fourth power of temperature, double the absolute temperature, and the radiant output skyrockets by 6. Thermal cameras shift our window, converting mid-infrared photons into visible images so we can see heat leaking from a house, a person's outline in darkness, or wildlife at night without a flashlight. In climate science, the balance between incoming sunlight and outgoing infrared sets the planet's equilibrium. Greenhouse gases don't block sunlight much, but they do absorb and re-emit infrared, delaying the escape of heat to space and raising the surface temperature required to balance the books. Clouds, aerosols, snow, forests, each changes reflectivity and emission in ways we can track from orbit because light carries both color and heat information. Again, speed is constant. Thermal photons don't crawl more slowly because they feel cozy, they move, but their wavelengths are longer, their energy smaller, and their interactions with matter different. Your skin senses heat not by tracking photon speed, but by absorbing more infrared energy than it emits. The night sky itself is cold in infrared, which is why a cloudless night can feel sharply chilly. Your body radiates to a dome that returns little radiative warmth. Pull a blanket over yourself and you change the exchange, not the pace of light. Comfort, in this sense, is a radiative accounting trick, abided by the same unchanging clock. At the single photon frontier, light becomes a tool for secrecy and computation. Quantum key distribution, QKD, sends individual photons prepared in specific polarization states across a fiber or free space link. Any eavesdropper trying to measure them unavoidably disturbs those states, introducing errors that the legitimate parties can detect. No faster-than-light trick is involved. Security comes from the quantum rule that unknown states can't be copied perfectly, the no-cloning theorem, and that measurements change what's being measured. On the lab bench, single photon emitters, quantum dots, color centers in diamond, trapped ions. Let researchers craft light one quantum at a time, testing the boundary between wave and particle with exquisite control. Entanglement extends the game. Two photons created together share correlations so tight that measuring one immediately lets you predict the outcome on the other, no matter how far apart they are. But as we've said, those correlations don't carry controllable messages. You still need a slower classical channel to compare notes, and that channel obeys. In quantum computing, light can be both messenger and qubit, guided through beam splitters and phase shifters to enact logic as interference patterns. Loss and noise are formidable enemies, but the appeal is clear. Photons don't decohere easily, and they're natural for networking. Across all of this, latency is a brick wall you can paint but not move. A quantum key exchange with a satellite still takes milliseconds to and from orbit. A metropolitan fiber link still waits microseconds per kilometer. The payoff is different: integrity, not speed; guarantees, not shortcuts. It's heartening that the same constant that caps how quickly we can talk also underwrites how safely we can whisper. Limits aren't always cages. Sometimes they're rails that let us build higher without falling. Why does it have the value it does? Physics answers with relationships, not reason. Falls out of the permittivity and permeability of free space. Constants that describe how electric and magnetic fields live in vacuum. With other constants and new characters emerge, the fine structure constant, IR, all rate of 137, a dimensionless measure of how strongly light couples to charged particles, Planck's constant, which quantizes action, Newton's, which sets gravitational strength. Change any of these, and you likely break chemistry, stars, or structure formation. In that isn't a number lying on a dial we can spin freely. It's woven into a web of constraints that let complexity persist. Physicists sometimes work in natural units, show collapsing conversions, so equations show their bones. That move isn't denial, it's acknowledgement that these constants are bridges between our human-made units, not decorations on the laws. If you imagine a universe with a different, you must also ask, what happens to nuclear fusion rates in stars? To radiative cooling that lets gas clouds collapse into galaxies? The answer is ripple. Perhaps planets don't coalesce, or maybe atoms don't hold stable shells, or light can't escape dense matter to cool it. Our universe balances on a scaffold where constants collaborate in ways that permit long-lived stars, carbon chemistry, liquid water, and late-night curiosity. It's a quiet kind of gratitude to sit with. We don't know why the scaffold is this one, but we know that because it is, photons can ferry information without wrecking causality, matter can organize without flying apart, and time can have a direction we can live with. That makes it feel less like a speed and more like a promise. Before a photon leaves the sun and kisses your cheek, it likely lived a very different life. In the core, fusion stitches hydrogen into helium, releasing energy as gamma-ray photons. But those newborn photons don't stream straight out like arrows. They random walk, scattering off charged particles, getting absorbed and re-emitted, changing direction and energy countless times. The journey to the surface can take on the order of many thousands to hundreds of thousands of years. A diffusion through dense, hot plasma, where the concept of a direct path barely applies. Only when that energy reaches the photosphere do the escaping photons take the near vacuum express, sprinting the 150 million kilometers to Earth in about 8 minutes. It's a humbling contrast, an eternity of meandering inside, then a blink of punctual flight across space. The sun's outer layers also modulate the light. Convection cells the size of continents bile and churn, imprinting granulation on the surface. Magnetic fields thread the plasma, darkening sunspots and sparking flares that can brighten and harden the spectrum briefly. The spectrum that reaches us is close to a black body curve around 500 T, but sprinkled with absorption lines from cooler gas above the surface. On its way to you, some wavelengths are nibbled by Earth's atmosphere, water vapor, oxygen, and carbon dioxide carve telltale troughs. Through a window in that filter, your eyes see a sun that looks white at noon and warmer toward the horizon, not because its photons slowed or tired, but because they scattered and thinned in air. Hold this picture as a lullaby. Light's story is often two stories, a patient, winding preparation written in matter and a fast, clean delivery written in vacuum. Both obey the same rules, both end for a moment in your perception, prompt, finite, and somehow timeless. Night sometimes writes its own light shows, and they're a patient reminder that photons are storytellers of charged particles as well as stars. Think of auroras, curtains of green, red, and violet that sway above polar horizons. The sun breathes a wind of charged particles. Magnetic storms fling some of them down Earth's field lines toward our atmosphere. As these electrons and ions rush in, they collide with atoms and molecules high above us, exciting them like plucked strings. When those atoms relax, they emit photons at very particular colors. Oxygen glows a soft, familiar green, and higher up where collisions are rarer, a rare red. Nitrogen offers blues and purples at the fringes and in rippling edges. The shapes, arcs, rayed bands, coronas that flare overhead are geometry traced by invisible field lines, written in light that falls at the same unchanging speed as every other photon we've met. Nothing about the dance requires shortcuts or broken rules. The incoming particles move fast. Yes, some at a respectable fraction of light speed, but still far below it. Their energy becomes a rain of colored photons launched into your eye at exactly the pace causality permits. Even the way auroras flicker is slow by the universe's strict metronome. Collisions, excitations, and decays happen on humanly gentle timescales, letting the display feel alive without ever outrunning the limits that keep cause ahead of effect. Walk a little farther into the scene and you can read more pale ripples reveal where the atmosphere thins, sudden brightening hints at substorms where magnetic energy reconfigures and releases. Tilt a camera with a polarizer and the glow won't vanish, but reflections on snow and ice may soften, letting the curtain stand out more clearly. The whole spectacle is a correspondence course between star and planet, translated into photons, delivered with perfect punctuality by a messenger that never changes its stride. If you want to talk across the solar system, you must learn to write with light and wait with grace. Deep space missions use big dishes and laser or radio transmitters to fling tightly organized photons back and forth. On Earth, giant parabolic antennas cup faint whispers. On a spacecraft, high-gain dishes or optical terminals aim a pencil-thin beam at a moving target the size of a coin from tens of millions of kilometers away. The channel must be robust. Cosmic rays flip bits, solar storms hiss static, and pointing errors nibble at signal strength. Engineers answer with error-correcting codes, patterns that scatter information across many photons so a few losses don't ruin the message. Read Solomon codes, convolutional codes, low-density parity check. They sound like busy work, but they are the poetry that lets a rover's panorama or a probe's magnetic squiggle arrive intact. Bandwidth is precious, power is scarce, geometry is everything. As Earth rotates, ground stations hand off the link like runners, and when the sun sits between us and a distant craft, communication may pause rather than shout through hot static. Under all these tactics sits latency, unbudgeable. Mars at a good day's alignment still means minutes for a round trip. A craft at Jupiter adds dozens of minutes. The Kuiper Belt asks for hours. You can compress images, prioritize science, and cache for later, but you cannot make a photon cross space faster than. So mission designs bend around that truth. Rovers get autonomy to avoid rocks without waiting for instructions. Orbiters buffer data and trickle it home when geometry is kind. Even on Earth, content delivery networks mimic the same lesson, placing copies close to you so the last leg, the one that must be run at light speed, is short. Communication becomes choreography, careful scheduling, small polite packets, and a calm respect for the tempo the universe imposes on any conversation worth having. Light is not just energy and information, it's meaning. Artists have known this longer than physicists have named it. Walk into a cathedral at noon, and you'll see stained glass curate the sun, filtering the spectrum into jewel tones that fall on stone, turning angles and dust into colored air. Each pane is a narrow band teacher. Reds survive where blues are absorbed. Patterns bloom because glass makers learn to scatter specific wavelengths with just the right impurities and bubbles. Painters invented languages for the same truth. Chiaroscuro, the play of deep shadow against bright light, is a meditation on how photons sculpt faces and objects, where the soft fall-off of illumination, inverse square law, lifts form from flatness. Golden hour is cinematography's love letter to blackbody radiation. When the sun sinks, its light shifts to longer wavelengths and filters through more air, softening contrast and bathing skin in kinder red. Directors use color temperature to cue emotion, cool blues for detachment, warm ambers for intimacy, while gaffers hide polarized reflections and shape beams with flags and silks to coax edges into the shot without harshness. Photographers set white balance not to lie but to choose which light to call truth in a world where lamps and skies disagree. LED eras bring new palettes. Flickerless, tunable spectra that mimic tungsten one moment and daylight the next, each with its own index of how faithfully colors render. None of these practices change light speed, they change its story. We alter spectra, angles, and surfaces to make the same punctual photons reveal different facets of the world. When a face looks tender beneath a lantern, the physics underneath is constant, a distribution of wavelengths, a gentle fall-off with distance, a sensor, eye, or camera integrating over time. The tenderness is ours, but it rides on the back of a law that never hurries and never delays, carrying mood at exact. Space-time diagrams are like quiet maps of what can touch what. Draw time as the vertical axis and space as the horizontal, and a single event becomes a point from which two cones unfold. The future cone, what your signals can reach, and the past cone, what signals could have reached you. World lines. The histories of objects thread the page, leaning more or less depending on their speed. Light lines tilt at 45 bursts in such diagrams. If you choose units where 1 second equals 1 light second of distance, nothing can tilt more horizontally without stepping outside the future cone, which is to say, without asking for impossible, faster than light influence. Minkowski taught us to stop separating space and time as if they were different species. He introduced the space-time interval, a blend that stays the same for all observers. Time-like separations inside the cone allow cause and effect. Space-like separations outside forbid influence. Light-like separations on the cone are the limit where photons live. Proper time. The time a traveler's own clock measures is the length along a time-like world line, and it maximizes for the straightest path between events. That's the geometric heart of the twin paradox. The twin who accelerates and turns around traces a kinked world line and experiences less proper time than the one who cruised straight, even though each saw the other's clock slow during the separated portion. It's not a trick of perception, it's geometry. What feels like a paradox dissolves in the diagram, exchange of simultaneity, a bend here, a rejoining there, two different world line lengths between the same bookend event. It's comforting in a way to see causality and limits become pictures rather than riddles. Light's cone isn't a wall so much as a clean margin on the page, keeping narratives from scribbling across one another out of order. Within the margin, endless stories beyond silence, not by decree but by the quiet grammar of space-time. You can measure light speed with kitchen tools and a little curiosity. One classic approach uses a microwave oven and a chocolate bar. Remove the turntable so the bar doesn't rotate. Run the microwave on low for a few seconds until you see melted spots form. Those hot spots mark antinodes, standing wave peaks where the electric field is strongest. Measure the distance between adjacent melted spots. That's half a wavelength of the microwave radiation inside, typically about 12 centimeters between peaks. Look up your oven's frequency on the label, often around 2.45 gigahertz. Multiply wavelength by frequency, and you'll land close to it. It's delightfully imprecise, but deeply satisfying, dessert as metrology. If you prefer lasers, set up a simple time-of-flight experiment with a long hallway, a mirror at the end, and a photodiode tied to an oscilloscope. Fire a short pulse, even a sharp LED blink can do. Catch the reflection and measure the delay. Have the round-trip time and divide distance by that to estimate. Urban constraints make the numbers small and the errors big. But the principle is clean. A photon leaves, a photon returns, and the gap between ticks is the story of space. For the ambitious, A Foucault-style rotating mirror setup compresses a huge distance into a compact bench by turning angle into time, swivel the returning beam just enough that a screen displacement translates to microseconds of flight. However you do it, the same humility applies. Measure carefully, average many times, and respect the fact that you're trying to catch the universe's fastest courier with tools built for slower days. The beauty of these experiments isn't their precision, it's the way they put the constancy of into your hands and eyes. You taste it in chocolate, see it in a jittering trace, and feel in a very human way that the limit isn't only a number in a book, it's a rhythm you can witness at home. The twin paradox earns its name only until you sit with it long enough to see it as a lullaby about geometry. Imagine twins, Anna and Ben. Anna stays on Earth. Ben rockets away at relativistic speed, coast, then turns around and returns. Each sees the other's clock tick slowly during the outbound and inbound cruises, a reciprocal effect of relative motion. Where's the asymmetry that makes Ben come home younger? It hides in the turnaround. Ben's frame changes. Lines of simultaneity, the now slices he uses to label distant events, swing dramatically during acceleration. On a space-time diagram, Ben's world line kinks, Anna's remains straight. Proper time along a world line is like the length of a path between the same two events, parting and reunion. The straight time-like path maximizes proper time. Anna ages more, Ben less. No message outruns light. No rule is strained. GPS satellites whisper the same lesson every day. They are Anna and Ben in miniature, their clocks offset by both speed and gravitational potential. Engineers pre-correct frequencies and apply continuous adjustments so your phone's trilateration doesn't wander. In particle physics, muons are born high in the atmosphere. They should decay before reaching ground if you compute with our clock, but in their own slowed time they live long enough to arrive. The paradox dissolves into a soothing moral. When what happened when depends on motion, you need a geometry that keeps the stories consistent. Special relativity supplies it with invariant intervals and cones. General relativity adds curvature, so gravity plays by the same logic. Keep the picture in mind. Clocks as rulers laid along world lines, each measuring its own journey honestly. There's something peaceful in that honesty. No clock lies. Each tells its truth about the path it took. Differences at reunion aren't betrayals. They're signatures of a universe that values path and pace, stitched together by light's unbending limit. On the grandest scales, light helps us measure the universe's growth. Edwin Hubble and Georges Lemaitre found that distant galaxies' spectral lines are redshifted in proportion to their distance. Recessional velocity increases with distance, a relation now framed by the Hubble-Lemaitre. This isn't galaxies tearing through space so much as space itself expanding, stretching the wavelengths of photons en route to turn redshifts into distances. Astronomers climb a calibrated ladder. Parallax anchors the nearest rung. Cepheid variables and other standard candles extend reach within and beyond our galaxy. Type Ia supernovae, thermonuclear bright candles, bridge to cosmological scale. Then come standard rulers written into the universe, baryon acoustic oscillations, BAO, primordial sound waves, frozen into the distribution of galaxies, imprint a characteristic scale we can measure in vast survey. The cosmic microwave background encodes an even earlier ruler in its model temperature pattern, a yardstick from an infant cosmos. Compare these rulers across redshift, and you read the expansion history, how the cosmic scale factor has changed with time. The plot, as always, is written in photons when they left, how their colors shifted, how many arrived from place to place, and as that plot sharpened, another character stepped forward. Dark energy, a name for the observed acceleration in expansion, inferred because distant supernovae were dimmer than a simple decelerating model would predict. Light didn't tell us why space accelerates, it told us that it does. Through it all is the anchor that lets time-dated light become distance. A redshift is a stretched wavelength, a distance is how far given light's pace has space grown while the photon traveled. The algebra looks dry, the intuition is soft. You can look deeper not by peering harder, but by listening longer to light that began its run when the universe was young and now arrives right on time. If you spend an evening with a cinematographer, you'll hear physics tucked into the jargon. Flags, nets, and bounce tools to sculpt inverse square falloff and tame specular highlights so eyes sparkle without blowing out skin. Diffusion softens hard point sources into larger apparent emitters, spreading shadows. Barn doors trim spill, scrims gently cut intensity without shifting color. Color Rendering Index, CRI, and its modern cousins tell how faithfully a lamp spectrum reveals objects' hues. High values mean fewer awkward surprises when a blue shirt turns gray on camera. Practical lights visible in frame are chosen not just for style, but for spectral honesty. A tungsten practical is warm and continuous. An LED practical needs good phosphors to avoid green spikes that skin will betray. Day for night grades lean on color, temperature, and exposure to fool the eye into reading cool and dim as night, exploiting your brain's constancy tricks. In architecture, clear stories and light wells do with stone what a gaffer does with flags. They guide photons, soften glare, and create luminance gradients that make spaces feel alive. Museums guard against UV to protect pigments. Galleries tune warmth to flatter canvases. Concert halls consider how light and sound share surfaces. Even the way we feel in a room leans on spectrum. High blue content can wire you awake. Low, warm light invites winding down. Smart bulbs mimic sunset because your circadian sensors listen to short wavelength with special attention. All this is delicate choreography around a constant tempo. You can bend a beam with a lens, break it into colors with a prism, reflect it with silk, absorb it with velvet. You cannot make it sprint. The best artists don't try, they accept the tempo and compose within it, asking light to reveal rather than rush, and trusting that a patient photon is still the most persuasive storyteller a scene can have. At this point, the speed of light may feel less like a ceiling and more like a kind of fairness woven into reality. Signals don't cut in line, they wait their turn across distance. Causes don't sneak behind effects. They arrive in order. Knowledge doesn't appear everywhere at once. It ripens outward from an event at a fixed pace. There's humility in that. When a star explodes in a galaxy 50 million light years away, its first light is already ancient news by the time it touches our telescopes. Yet it is news to us exactly when it should be. Not earlier, not later. When you message a friend across the planet, the round-trip delay is a tiny echo of the same principle, a gentle reminder that even in our quick world, there is a minimum time to anything honest. You can treat that as a nuisance, or you can treat it as breathing space. The limit gives designers time to add checks, pilots time to confirm, and minds time to consider. It gives astronomers a way to turn distance into chronology and turn faint colors into the rise and fall of universes. It gives engineers a clean target, a number they cannot beat around which to design resilient systems. And it gives poets a metaphor that understanding itself is like light. It travels, it takes time, and it is worth the wait. If you ever feel the tug to wish the limit away, imagine the tangle without it. Messages arriving before they're sent, choices colliding with causes, histories in contradiction. The lean we sense in the night sky, the sense that the story holds together, leans on the fact that photons keep perfect time. This far, no farther sounds stern, but it's also merciful. Boundaries make meaning. The speed of light does not taunt us. It tethers us gently to a universe that can be known. So we end where we began, with a simple question that opened into a long, soft walk. Why does light have a speed limit? Because the universe is built that way, not capriciously, but coherently. Maxwell's equations say a self-propagating dance of electric and magnetic fields must move at a specific pace set by the vacuum itself. Einstein says that pace is the same for everyone, always, and that time and space will bend to protect it. Geometry says that pace draws cones on the map, clean boundaries between can and cannot, before and after. Technology says that pace is a ruler we can trust to route the internet under oceans, to keep clocks in satellites honest, to time the quiver of space-time in giant interferometers. Biology says that pace is a partner setting circadian rhythms, painting sight, powering leaves. Art says that pace is a muse leading rays through glass and film, pouring meaning over stone and skin. And your life says that pace is a comfort, a minimum waiting time that makes room for care. Through every chapter, photons remain themselves, massless, restless, always in motion, never cheating, never late. They bent around suns, scattered in skies, whispered in microwaves, stitched galaxies into maps, and still arrived at your eyes with ordinary grace. If this journey kept you awake a little, I hope it did so gently, not with urgency, but with a quiet permission to wonder. And if you're drifting off now, let the last thought be simple. Somewhere a photon just left a star, somewhere another just touched a sea, somewhere a deep space dish just caught a handful from a robot on a red world, somewhere a candle sent one more to the page you're reading. All of them moved at the same steady pace, a lullaby tempo for a logical universe. If you enjoyed this slow exploration, a like and a subscribe help more sleepy minds find their way here. For now, rest well, and may your dreams keep perfect time.